In the second half of this unit, in the second video for this unit, I want to say a little bit about basic sedimentological techniques and the ways in which physical geographers can use the characteristics of sediments to tell us something about their history and their origin, the processes by which they were created and deposited. So, for example, you might look at a well-rounded stone like this and you'd think, well, that hasn't been freshly chipped off a rock surface by a hammer or by frost shattering. That wouldn't give it that well-rounded shape. And you might imagine that something like rolling around in a river in water might give it that well-rounded shape, and you wouldn't be wrong. By contrast, this angular, sharp bit of rock, well, that does look like it was just hit off with a hammer or broken by frost shattering or hit by a boulder in an avalanche, chipping another bit of rock off the mountainside. So just in a very common sense kind of a way, you can look at the shape or the morphology of a clast, which is a broken fragment of rock or a piece of rock in a sediment. You can look at the shape of a clast or the characteristics of a part of your sedimentary sample, and from that basic first glance common sense look, say, yeah, this looks like it might have been this or it might have been that. So if I say we had a lot of wind yesterday and the wind was picking up debris and blowing it around, and I say, yeah, because look at the debris, or if I say, yeah, because look at this debris, you kind of have an idea which kind of debris was most likely to have been being blown around, and therefore what kind of sedimentary deposit you'd be likely to find from shallow water washing around or from a windy day. And if I said, oh, a glacier, you don't need to sound like a glacier or a massive flood to bring this boulder into position, then you'd say, yeah, for that size of boulder, you're going to need this size or this amount of energy in the system to start moving that around. So lots of common sense kinds of ideas. And some particular processes have particular clast morphologies associated with them. So this actually is a glacially transported bit of rock. Pull this up from a field just near my house, and from one angle it looks fairly well rounded, like this first rock I showed you, but then as you turn it around and start looking at it, you can see these facets or faces that have been smoothed onto it, and that's because the rock has been dragged along underneath the glacier, rubbing against the ground, or has been embedded in the ground and other rocks have rubbed across it. And sometimes in this rock, for example, if you get the light just right, you might have to take my word for it, you can actually see scratches on the rock that have been left behind as a glacier has dragged other rocks across them or has dragged that rock across the substrate underneath it. So there are characteristics of various kinds, either in individual clasts or in amounts of debris, amounts of sediment, that tell you something about the process that must have brought it there. For example, there's a photograph here of a stream flowing across the front of the Athabasca Glacier in British Columbia. If you just look at that photo and I was to ask you, where do you think the stones in that stream have come from? And I give you a number of hypotheses. They might have all fallen off the mountainside and avalanched or cascaded down the mountainside, gone down a scree slope, frost shattering, breaking rocks off the hill slope surface. They slide down into the river and the river carries them away. Or maybe they've been carried underneath the glacier. They've been transported subglacially, going through those processes I mentioned previously, and then emerged into the river. And maybe they emerged into the river very nearby, or maybe actually this river has been travelling a long distance around the back of the glacier, around the front of the glacier. And over that long distance of travel, these rocks have been changed a lot during that process, during those processes. So what evidence could you look at in the individual particles or in the nature of the sediment overall to tell you something about where that debris has actually come from? What's the origin of that sediment? So one thing that you might look at is the size of your clasts or particles or grains. Are you dealing with boulders or cobbles, gravel, silt, clay, etc.? And it's not just the sizes of individual boulders, but the distribution of particle sizes within your sample. Is there a very wide range of sizes with clay, silt, sand, gravel, cobbles and boulders all in the same sample? Or are they very well sorted so that you only have gravel or you only have silt? Is it unimodal, one peak on your graph of distribution, so it's all sand? Or is it, for example, bimodal, where you might have lots of silt, not much sand or gravel, then lots of cobbles? So there are lots of different distributions of particle sizes that you might have within a sample. There are various scales that geomorphologists use to describe their particle sizes, such as this one, the Wentworth scale, which separates out different descriptive terms, boulders, cobbles, gravel, etc., at different size fractions, and other scales such as the phi scale, which is a logarithmic scale where 1 millimeter is 0 phi or 0 phi, and then 1 micron would be 10 phi, and 64 millimeters, the cobble gravel boulder, would be minus 6 phi. And that just works well if you're plotting your results on a graph, as you'll see in a second. And if you've sampled a few kilograms of sediment from a riverbed or a beach, this is how you might plot up your data, either just marking size grade by size grade how much of your sample was accounted for by each size grade within your categories here. So how much was very fine, how much was sand, how much was gravel, how much were pebbles, and so on. Or you can do it as a cumulative value, which shows always going from 0 up to how quickly you get to your 100% level with your different particle sizes. And the shapes of these curves or these columns tells you about the distribution of particle sizes within your sample. And this is very typical of the kind of data that you might find yourselves presenting later on if you do a dissertation research project looking at sedimentological characteristics of rivers or beaches or glacier forelands or whatever environment you're interested in. Another characteristic that we might be interested in is the sorting of our grain sizes. So, for example, in a well-sorted sample, the grain sizes are all very similar. You've got lots and lots of sand and not much else, or you've got lots and lots of gravel and not much else. In a poorly sorted sample, you have more of a mixture, some bigger particles, some smaller particles, fine-grained, coarse-grained. This diagram also illustrates the difference that we've mentioned previously in the particle shapes that you might find between rounded in these upper examples and very angular in these examples lower down. And that classed roundness is another very important way of looking at clasts, looking at particles, and inferring something about their transport or depositional history, as we spoke about earlier when we were looking at the examples that looked as if they might have been chipped straight off a rock face, and the examples that looked as if they might have been rolling around in a river being polished by sand and other pebbles for a long time. And the most commonly used simple scale of roundness is the Powers scale, which goes from very angular through angular, subrounded, rounded, and well-rounded. And geomorphologists would make inferences about the process histories and depositional environments based on that roundness scale. Now, there are lots of different ways of looking at the shape of a rock, and one thing that geomorphologists tend to do is measure the long axis, the short axis, the shortest dimension across a pebble, and then that intermediate dimension, and they're called the A, B, and C axes of a cluster of a pebble. And you can use the ratios between those A, B, and C axes to define clasts on a graph like this. This is the Zing sphericity diagram, and it separates out particles of different approximate shapes. So a cube or a sphere, a tennis ball, that would end up in this corner of the diagram, spheroidal shapes. If they're flattened out but still have the broad in those two dimensions, then we have discs, either round or square. That isn't the point. It's just looking at the ratio between the A and B axis versus that C axis. So these flattened shapes are discs. If they're flattened and very elongated, then we'd call it a blade. And if they're elongated but not so flattened, then we'd call it a rod. So rods, discs, blades, and spheroids describe the basic shapes of particles that we can get. Combine that with the roundness scale and think about incorporating that with sorting as well, then we begin to be able to put together some kind of story about what is likely to have happened to generate a sediment with these kinds of characteristics. There are other things that we can look at as well. One of them, for example, is clast fabric, which is all to do with the orientation of either the clasts within a pile of clasts or the orientation of larger clasts within a finer matrix. So if you think, for example, of a typical glacial till, formerly called boulder clay, in the fairy book image of what boulder clay or till looks like. It's big boulders suspended in a matrix of clay and sand. And you can measure the orientation of those bigger boulders or the clasts within the matrix. And one particular fabric pattern that is a very nice example of how you can use fabrics in a very straightforward way is this particular pattern, which is called imbrication. And you can see here that these rocks, which are part of a riverbed, this is the water at low flow, so it's revealing a little bit of the bed or revealing a little bit of the channel where these particles have been deposited and moved around by water. But look how the long axes of most of these boulders are all orientated in a similar kind of direction. And you can almost imagine if you ran water across those really fast in that direction, well, that would reinforce this. It's almost like a streamlining in the pebble orientations, or the rock orientations. But if you flip the flow around and flowed the water that way from left to right very rapidly, you could imagine it would get underneath these rocks and flip them over so they'd be pointing the other way. And that's exactly what's happened, that under higher flow, these particles have been reorientated or have been deposited in a particular orientation so that we can read the former flow direction at the time of last time these boulders were mobile. We can read what direction the water was flowing in. Now that seems like a fairly useless thing when you can see the river right there. But if you're looking at ancient sediments left behind by a river which is long gone, then being able to work out the flow direction from evidence such as this can be really useful. Now, geomorphologists often talk about strong or weak fabrics, and what they're talking about there is whether most of the particles do seem to be aligned with their long axes pointing in one direction, or whether they're not very well aligned and they seem to be pointing all over the place. A lot of the work that's been done on this has been looking at glacial deposits known as till, and so people often talk about till fabric analysis as a nice straightforward example of how this kind of fabric analysis can work. You'll often see diagrams such as this. We have a circle with lots of dots in it. The way to imagine this diagram is that someone's got a bowl and you're looking down into the bottom of this bowl. They're then pointing the particles in the orientation that they were aligned within their sediment, and you can almost imagine that each particle is a torch, and the little dot is where the light is pointing from the end of this particle as you're holding it above your bowl. So basically each dot indicates where the end of the long axis of a particle was pointing. So you can see here, for example, all these particles were orientated pointing diagonally up in this direction and down in that direction, so that the torch beam, if you like, for all the particles was shining in pretty much the same area of this part of the bottom of the bowl. But this other side is not quite so well focused, if you like, so this sample isn't quite such a strong orientation. Here's a really strongly orientated set. And different types of sedimentary environment lead to different patterns of fabric within the long axis orientations. So if a glacier has smeared particles down in what's called a lodgement till, that often leads to a very strong fabric where lots of the particles are pointing the same way. But if you have what's called a melt-out till, where a glacier has just released debris in a very wet situation, it's flowed around in all sorts of different directions without any really strong pressure on it, then we have a very weak or disorganized fabric in that till. So by looking at the sediment that's left behind after the glacier has gone, we can work out something about the environment in which those deposits were made. So these kinds of diagrams are sometimes referred to as lower hemisphere projections, because you're looking into the bottom half of a sphere, or looking down into the bottom of a bowl and seeing the orientations where the ends of your particles were all pointing to. Now, if you look on Google Earth or the NASA Earth Observatory site, or lots of other sites where you can find air photos and satellite images over regions where there's lots of sediment transfer going on, you can get a feel for the importance of sedimentology in understanding geomorphology, understanding the way that Earth's surface processes and landforms work. I'm not going to talk about these in detail, but you might want to chase them up in your own independent research. So here's a satellite image here of the Copper River in Alaska from the Earth Observatory website. And what's happening here is that we have a glaciated environment, a river coming out of that environment carrying a lot of sediment. And in this particular image, the wind is picking up the sediment from the valley and blowing it out into the ocean. So not only are the glaciers producing sediment and putting them into the ocean or into the rivers, and not only are the rivers producing sediment and putting them out into the ocean, but also the wind is picking up that sediment and also transferring it out to sea. So there are lots of different mechanisms by which the Earth's surface is being denuded, worn down, and the sediment is being transported or transferred out into the ocean. This is another image of the same location showing that the glaciers and the rivers in a little bit more detail, because there isn't so much wind blowing the sediment around in the atmosphere in this image, so you get a much clearer shot of what the rivers and the glaciers are doing. But it just illustrates that at different times, different parts of the sediment transfer system will be working to greater or lesser effect. So it isn't always windy. The rivers aren't always in high flow regime. Glaciers on a long time scale aren't always melting and retreating. So different things are happening at different points in time, and so we can have a very complex record of sediment transfer over long periods in the sedimentary record. Earlier in this module, we used an example of rivers coming out of the Himalayas and onto the lowlands downstream and depositing their sediment in these huge alluvial fans. You can expand that case study now and have a look, for example, at the Bay of Bengal, where a lot of these rivers from several of these rivers from the Himalayas eventually make their way out to sea in this region, and you can see a huge amount of sediment being deposited in the northern end of the Bay of Bengal. And a really interesting and exciting thing for you to do is just to go and explore Earth Observatory, Google Earth, just have a look around and find lots of different environments when you can see the things that we've been talking about actually going on. You can see erosion, transport, deposition. You can see evidence of processes on the surface wearing down the land surface, putting sediment into transport in rivers, in glaciers, in the atmosphere, pouring it into the oceans. And sometimes you can even see in these satellite images where that debris is going in the ocean. And so you can see the whole sediment transfer system, and you can really begin to get a feeling for geomorphology. The things that we've been talking about over those last few slides, they actually boil down to geomorphology. Geomorphology is an important part of physical geography, and it's an important word for you to become familiar with at this stage if you aren't already. Geomorphology is the science of landforms, landscapes, and the processes by which landforms and landscapes are created and modified. So if we're thinking about erosion, transport, deposition, if we're thinking about uplift of mountain ranges and the long-term denudation of those ranges, if we're thinking about weathering of rocks, if we're thinking about the deposition of sediments either on land or even in the deep oceans, if there's some long-term impact of that on landforms and landscapes. So geomorphology, the science of landforms and landscapes and the processes that create and modify them, a really important part of physical geography, and we'll be using it later in this module to tie together some of our ideas about environment, climate change, processes, the links between the big global system and local events in the world around us. Geomorphology is a very useful way of tying together some of those ideas, because our local landscapes are in many cases controlled by global processes, and the interaction between energy and materials at the Earth's surface generating processes, well, that's an underlying theme for our module as a whole, and it's also a really important way of understanding how landforms and landscapes are made. So geomorphology is going to be a really important case study from now on throughout this module. So that brings us towards the end of this section. As always, make sure you go back and do the basic reading, check through the notes that you've taken in these sessions, and make sure that you understand some of these basic distinctions and basic definitions that we've been talking about. Also, don't forget to do the basic reading. The lectures or the online units that we're providing are really just signposting for you and giving you an idea of what the important issues are that you need to find out about. We're giving you a little bit of information, giving you a few examples to get you started, but it's reading, which is how you'll really get the information that you need to add depth to your knowledge and understanding of these topics. So I'm just going to finish off leaving you with these key points that I showed you at the beginning of the first half of this session, just so that you can read through these one more time and just make sure that you have understood the key points that we're trying to make about sedimentology, sediment transfer and earth surface materials at this point in the module, before we move on next time to talk about atmosphere and the oceans. All part of our big story about how energy and materials interact at the Earth's surface to underpin the basics of physical geography.